this about? Is recording, right? Yes. Okay. So what is this about? A seminar about norms and distances. Why? Because in many times you need to do some calculation and you have to calculate some distance or some norm, and you don't know exactly which one do you need for the specific cases. And also there are some times that you are reading a paper, some random norm appear there and it's not defined, and you have to have the intuition about which one is the one they are using. So it's little bit thinking outside the box. So let's start by typical first year bachelor's linear algebra course, which is defining what are distances. So a distance is just a function that takes two elements of some vector space, which, so this X and Y belongs to some vector space, I will call it S, and it gives you a distance which is just a real number. So this is very basic. But it needs to fulfill four properties. The first one is the triangle equality. So x squared be less than equal x plus b. So this, the intuition behind this property is just that the distance between 2 points should be bounded by the sum of the distance with the perspective of other points. So this is why this is called triangle inequality, relatively simple. Then the other property is that this function should be symmetric in the sense that it is the same of calculating the distance from one point to another or the other way around. So this one is really simple. Then the distance to the point itself should be 0. This is again a relatively simple thing to think about. It's just if you are calculating the distance to itself, it must be 0. And this here is for all elements in the space. There is no restriction. And one important property of the distance is that it must be positive. So this is relatively simple, but there are some times in which you might want to drop some of the properties to still have some useful information. So this is distances. Now let's go to norms. So the norm is again another function. In this case, it only takes one element from the vector space, and this again will give you some real number. Now, the properties that we need for norms. One is exactly the triangular inequality, but now for norms, which is a little bit different. So let's call it now F. Then the other one is absolute homogeneity, and this is closely related with the fact that this should be somehow linear, and this tells you that if you multiply your vector by some scalar, the scalar add to the norm just with its absolute value. This, let's say, efficiency. I think there is no problem there. Again, in this case, we have non-negativity. So, can say that the norms always give you something that is greater or equal than 0.
One question for the distances, the fourth point already follows from the first three, or not?
Yeah,
or should that be
I think this is not needed, but it's to keep it in mind, because obviously I think you
Or should it be maybe
from this one and this one you can reduce the fourth one. I think
yes, what the Basque follow is having both that has to be strictly equal and 0 for different x.
Yeah, this was it. Yeah, maybe for different x and y, maybe you have that it's strictly bigger than 0. Maybe then, well, I don't know the definition. But
yeah, no. This I think that you can keep it. You can keep this equality, because this is a property that only refers to when you calculate the distance to itself. So this must be fulfilled, but you can also have something like this. So, for example, really say example. Have two axes, and your distance on the measure, the difference in this thing. So you can have 2 points here that are not equal, but the distance is also 0. So you can think about these stress cases in which you have to impose here the equality.
I think strictly speaking, some people will go that distance. But other people.
But this in fact is a distance, because I mean it doesn't come. I will talk about this later. But strictly speaking, it doesn't come from a norm, but still fulfills all the properties of a distance. Let's say this is kind of a clear distance is. This in fact is the clear distance if you only take one direction. So yeah.
I think some people in the belief of the distance they use that d of x1 by a rate of 0 and it's equal to the equality only happens if x equal if and only x equal to 1.
No, but this is what I'm saying, that not always happen, because in this case.
But it's definition. Yeah. The definition. So there is people that by definition already that is a distance. For different points, it's not.
I see that. Okay, yeah. But
there is people that by definition take the fourth property to be strictly greater than 1 for x and different. That's quite common. But you could call that a distance, these people would call that a quasi-distance, right? It is one of the properties, but not one of the things.
But in this case, I haven't seen. I think in the Wikipedia they allow for this.
Yeah, I mean, it is a part of the definitions.
Yeah, because for example, when people call some function a pseudo distance or whatever it is, maybe because this property doesn't fulfill. For example, if you have directed graphs, this is not fulfilled always, but you can still call this distance. Okay, so I'll go back to the norms. The only property left that here is positive semi-definiteness. which is that there is only one element that is equal to 0. And so this means that S equal to 0. So again, you might be using some norm that is interesting for your problem, but it's not really a norm because, for example, it might not fulfill this one, but still can be useful. So why I am telling you this? Because sometimes you really focus on, oh no, I have to calculate something according to some norm. Okay, maybe not. One example for a distance that is really useful but is not really a distance is the Hamming distance. Hamming distance is just taking two vectors and sum over the coordinates that are different. So it's something like this. So you see Hamming distance, for example, with binary vectors. If you calculate the Hamming distance over these two elements, equal to 1 because these two are non-equal. And this Hamming distance is really useful even in quantum computing. And just as another example, I can give you a kind of a distance that I have used in the Italian or whatever, but it's just saying that the distance between two vectors is the angle between them. This again is not a distance because, for example, I think it doesn't fulfill this one, not this one, because you can have positive and negative vectors. You can put some absolute value there. Usually, absolute value converts many functions to distances. But okay, there are many examples. Here in the notes, I have found some interesting distances. For example, working with probability distribution, you have, I don't know, Wasserstein distances. Can be useful in some cases. This is something that you have to look for yourself whenever you try to solve different problems. And now some definitions about some distances that I find interesting. One important thing that I forgot. Usually, whenever you have a norm, you can define from it a distance. So, for example, you have the Euclidean norm, you can define the Euclidean distance just by taking Euclidean norm, you can go to Euclidean distance x like this. So this is something that might be useful in many cases. However, whenever you have a distance here, it doesn't mean it always comes from a norm. And this is important because in the example that I gave to you, the Hamming distance does not come from a norm. So there are some subtleties here. Okay, so or also the like angle distance that I give to you also doesn't come from a norm. So this is something to take care of. Okay, so now let's go to some definitions of vector norms. These are distances, norms that are defined in vector spaces like this. Let's say N. So simple vectors, not matrices. And the common one and the most widely used is the general P norms, which is defined as let's see, write it well. So have to sum over all the elements in your vector, taking the power of P, and then the whole sum raised to 1 minus P. For example, if you take P equal to 2, you will arrive at the critical distance, the one that everyone knows. If you take P equal to 1, you will find something that is sometimes useful, which is just summing over the absolute value of the elements of your vector. Again, this is very useful sometimes. And another paradigmatic norm is the infinite norm, which infinite, you have to take the limit of this when it goes to infinity, but this is nothing else than the maximum value of the coordinate, maximum absolute value of the coordinates of your vector. And again, now we can see that there is some trick that is useful sometimes. We can go to, okay, for both, this is for P greater than 0, but we can go to negative numbers, even, can go to P equal to minus infinity. This won't be a norm, because there are some properties here that are not fulfilled. In particular, I think that this one is not fulfilled for the minus infinity norm, but this will tell you more or less the minimum value of any of your coordinates in your vector. So you can imagine that if you have a vector in which you have 1, 0, the minus infinity norm of that vector will also be 0. This is why it doesn't fulfill this property. But still is relatively useful, and maybe you can find some use to it.
But this is not always true, right?
So not always true.
This negative one always true.
Yes, this is always true. This gives you the minimum element in absolute value of your vector. However, this is not a norm. So this is the only thing. So I will put here last thing. This is not a norm. Okay. Useful thing about P norms is that you have the Holder's inequality that is useful to calculate things sometimes. You have to find it. So you have is just telling you that the absolute value of some inner product between two elements, so the typical inner product in vector spaces, is upper bounded by something related with its norms that fulfill this thing. And for example, if you go back to putting here P equal to 2, Q equal to 2, you will get the typical thing. which is that's algebra first year result. And
generalize this half an hour are not
1 moment. And then you have some here, you have some R here or whatever.
no, it's seen on the exponent.
Yeah. This is R. I haven't used the one with R.
Yeah, no, I think when you cover that there's so it's a norm of the R norm. The R norm of xy is smaller or equal than the P norm, but what's the R norm of xy? This is vector, sorry, this is vector with operators.
Yeah. So yeah, whatever.
No,
This is not right. Yeah. This is why I did. So this is typical. And just to end, to relate with what Ruben is going to tell you, is that you can also define some funny type of norms with vectors, which is really not very usual, which is one induced by a positive semi-definite matrix. So let's say you have this, which is positive semi-definite and symmetric. And now you can define the norm to respect with this matrix as the square root of x ax. If you want to go to clear states and A being for example, they could be useful somehow for some strange case. For example, this what tells you is that you can perform your unit disk. So now about unit disk. If you want to find which is the region that fulfills that the vector norm is equal to 1, if you use the typical Euclidean distance, you have the circle, typical. If you want to go to the 1 norm, this is a square. All the points in the square will have norm 1. And then you can go to different values of P. Let's say you have P equal to 500 and you will have something before. And in the limit of P equal to infinity, you will have a square rotated by 45 degrees. So you can see more or less the relation between the distances just by looking at them. What else? So for example, if you want, if you are using some A matrix in a two-dimensional space that looks like this, your unit circle will look like this. This is the intuition behind this kind of strange norms. And now, looking at this picture, we can see that there is some relation between them, which is usually very interesting. So let's see the relation between the P norms. This distance is the lower bound of the two distances. As we can see, the circle is bigger than this small square. This is also the lower bound of the x1, which is the maximum, the biggest one of them. And then you can introduce some dimensionality here and relate one norm with the two norms, or even with the infinity norm, where n is the number of the dimension of your vector space. And this is particularly interesting. Then you have another one that doesn't fit here, but is also useful. That is relating these both. So the norm 2 is lower upper bounded by the square root of the dimensionality of the infinite norm. And with this, I think that Ruben can introduce the element-wise matrix norms.
So, yeah, so the idea so far was to see, to start with vector norms. And now the idea is to move to matrix norms. So, maybe I will clean things a bit. Yeah, because there is not much space here. You can write
And I also checked the standard definition of the distance, and usually it's like a strict,
it's a strict.
strictly bigger than 0.
What did you mean on the holders?
Context inequality can be generalized for any norm, number of norms, that's the R norm of the product of S to the
Yeah.
modulus of the P, 1 over P, 1 over M. Smaller or equal to P and Q, and then you have to conditions.
Okay, but I will then move to matrix. This is missed. Okay, this is it. Okay, so for matrix norms, so now A, let's say A and B have some matrices. I think now we have seen how to some examples of vector norms. And now we want to have norms also for matrices because that's important, as we will see. The thing here is how do we do this? So the first thing we can do is an n by n matrix can be related with a vector in n squared, right? If you take, for instance, the element of the matrix ij. Okay, so all of these elements, we have n squared of them. We can see all of these elements as a huge column, right? When I do A1, 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 A2, A2, up to AN, AN. And now any norm that we have in vectors of this size, we can use it for this kind of matrices. That could be one approach. The problem with that approach is that it's usually not very useful. Because matrices have other properties. Usually you use matrices to act on vectors. And if you do norms like this way, often they don't have the kind of properties that you would expect. So for instance, one property, okay, I will introduce the properties later. But this will be one approach. I won't focus on this approach. So one more reasonable way to introduce, to define norms for matrices coming from vectors is the other one. So now let's say we have, okay, let me, yeah. Now these are matrices that go from n to n, okay? I will have some matrix norm, vector norm alpha, okay, for defined for elements in n, and you have some other vector norm beta for elements in C of n. Okay. So one way we can define a norm for A is the induced norm. Okay, so these are do, re, norm, which is you take two norms, one in the input and one in the input space and one in the output space, and now you get the supreme list. So for any input element, you compute this ratio. So this A is acting on X, so this is in the output space, so we can apply the output norm, and now divide by the linear norm of the vector. So this has to be different from 0, but that's okay. Okay, so this is one approach, the induced norms. What's the good thing about induced norms? They are consistent with the norms that they are induced by. So let's see. So now let's take some arbitrary x and see what happens with this thing. Okay. So, yeah, I'm using the same letter twice, but it's fine. So we can see that this is the alpha, right? Yeah. Okay, so what's the thing? If you move this thing to the other side, this is basically okay. So these ratios are these ones, right? And this induced norm of the matrix is the supreme norm of all of these ratios. So the induced norm of the matrix has to bound this ratio for any x in the input space. Okay? Yeah. Then now if you move x to the other side, you can see the value this way. Okay. This is super trivial, right? And why is this useful with induced norms? So now let's say that you have okay, so you have some matrix A0 and some matrix A that is very similar to A0. What do we mean by very similar? We mean that the difference in some induced norm defined this way is smaller than epsilon. So they are very similar. And now I want to know how similar are then these two vectors. To know that these two vectors are similar, what we need to say is that the norm of the difference is somehow small, right? So what we want to bound, these two things are similar if we can show that this, so this is in the output space, if this, we can show that this is small. And how can we do this? Okay, I hope to see that this is the same as and now using that property of for induced norms, we have okay, let's change the order, but this doesn't matter. Right? And now we use that this difference is small. And then the difference between these two vectors has to be also small. Right? So what's telling what that is telling us is if these two matrices are similar in some induced norm, then for the respective norms, vector norms, we can say that these two things are also similar. Of course, it depends on the size of x, because if I take x to be huge, I will be amplifying the difference between these two matrices a lot. But there is always this epsilon prefactor that is doing things. So this is why induced norms are more interesting than element-wise norms, because when I apply these matrices into vectors, I get interesting things. Okay. Yeah, sure.
To compute the first one. So okay, that's more.
Yeah, that's the tough part.
Okay.
Sure. Okay, so to compute this thing, it depends on the properties of your system, let's say. So for instance, you work a lot with Hamiltonian, right? So you have some H0 and some perturbation B. If you are lucky enough, this perturbation may have a small refactor, then the difference between these two in some norm is equal to this thing, and we show that norms satisfy this property that you can take the absolute value out, right? So now if you know that this lambda refactor is small compared to the norm of B, and then the difficult thing may be to bound the norm of B, that can happen, then you know that the difference between these two things is also small. So that would be one approach, for instance. But yeah, sure. This was assumed given. Okay, so examples of alpha and beta, we can take the p norms in the input and the output. So from P to Q would be supreme X. Okay, now I will assume that these are square matrices. I mean, there is no reason to assume this, but maybe it's easier. So we are taking Q in the end and P in the input. And these basically are the P norms that Mikel defined second of all. And very typically, if we take P and Q to be the same, they just use the split. So this is P. And this is the first problem with the notation of matrix norms. Because this matrix notation is used for the other norm that I will introduce later. Okay, so this is one with the notation. It's very common if you know that you are working with induced norms. It's super common to just use this notation and work with it. And forget that there is other people using this very same notation for a very different thing. So that's one of the cases where you have to be careful if in a paper they use this notation. You have to know which one it is. Usually from context it's easy to know, but yeah. Okay, so some examples. The one norm reduced to taking the maximum column. The maximum one norm of the columns. So this is J. And well, these are the columns or the rows? The columns, no? Right here. And the infinity norm is taking the maximum of the rows. And the two norm it's given by the maximum singular value. Does everybody here know what the singular values are? Please raise your hand if you know what a singular value is. Alats? Do you know what a singular value is? Yes? And Rob? No? Okay. Okay, so this is just the maximum singular value. Okay, very briefly, what are singular values? You know that for instance, you know that for a Hermitian matrix, you can define the eigenvalues, and then you have this structure, right? This is a unitary, this is a real diagonal matrix, and this is a joint of that unitary. Now, so this is Hermitian. Now, if A is an arbitrary matrix, you can't play this game always. Okay? There are some differences. But what you can do is realize that the matrix either A is okay, so and the diagonal elements, these are the values of H and the diagonal elements of this matrix, right? So the thing is that for any matrix you can define this other matrix, and now this matrix is Hermitian. And now this matrix is Hermitian, right? Because if I take the adjoint here, it changes the order, and you play the adjoint, so this is also Hermitian. So this matrix will have some decomposition as above. And this matrix will have some beautiful eigenvalues. that not only will be real, but they will also be positive in this case. Yeah, you trust me? Then these guys are the singular values of A. In particular, what you get is that you can find two unitary matrices that will be different in this case, and some diagonal matrix with only positive entries. S, well, it's not, yeah, it's more or less, you can think of it as diagonal with these entries here. Okay, so these two given by the maximum singular value. Okay, so this would be about induced norms. And now that we introduced singular values, I can introduce the certain P norms easier. Okay, I will erase this thing. So this whole thing about norms is about measuring the size of things, right? So, well, the square root of this guy is the singular value. Okay. Okay, so if we have an Hermitian matrix, this whole thing is about measuring the size of things. So if we have an Hermitian matrix, one way to measure the size of things of the matrix itself would be to add all the eigenvalues, right? We could, so for some matrix, Hermitian matrix A, we could take all the eigenvalues and add them up, for instance. This could be a reasonable way to measure its size. And in fact, we can use the eigenvalues of H and the definition of any vector norm on them, right? So a P norm, for instance, to do this trick. Okay, so certain P norms, you can think the motivation of certain P norms or something like that. But to define them for arbitrary matrices, we use the singular values instead of the eigenvalues. So the certain P norm of a matrix A is just the P norm of the singular values, which is given by, okay, let's write it these two ways. And this, by this property here, it's easy to see that it's the same as, let me see, is this like this? No, right? Square. Okay. So these two things are the same. And these are the certain P norms. And this is why I was telling you that the notation. This same one? Those are the singular values of A. Okay, so it's the sigma, I'm using sigma as a notation. To the power of P. So this is basically the P norm on the singular values.
So there's a square root, no? And the P is
Outside. Yeah.
outside.
Yeah. Okay. Yeah.
The TNS notation is outside the yes.
Yeah, okay, yes, you could also write that, but I prefer because, I mean, you define, that's fine. It's okay. Okay, so, first things first, okay, so the singular values of a matrix, they don't change if you apply unitary, to the right and to the left, right? So the matrix, okay, singular values of A are the same as the singular values of UA and are the same as singular values of A. Applying unitary relation doesn't change the singular values. Why? Because this decomposition won't change, so it's easy to see that, well, the composition will change, but you only change these unitary things. You don't really change this diagonal matrix in the middle. So by this same property, the certain p-norms satisfy that they are unitary invariant. And in particular, if you apply a unitary conjugation, they are also preserved. So you can apply them both, and they are also preserved. So this is a quite good thing about these norms for matrices, because it doesn't matter if what basically represent the norm, it will always be the same. Okay, so apart from this, let's go to some examples and the properties and what they are useful. What time do we have here? Oh, which is now?
No, I mean,
12. Okay. Okay, so in some cases, the two norm, if we use this notation, it's basically. Yeah.
So, if that norm is unitary.
Unitary.
Yeah. Doesn't that mean that for any matrix the norm is always the same? Or not? Because I would expect that I can achieve any matrix by unitary.
But you cannot.
You cannot. Okay.
You cannot. No, because if those singular values, they are like the invariant thing under your case. So if you take the diagonal matrix, let's say 1, 2, 0, 0, and you apply unitary things here and there, the singular values of these matrices will always be 1 and 2. You cannot achieve any other thing.
yeah, because it's already diagonal.
And you can complete yourself pretty easily with the extreme example of if you have 1, 1, and you apply some unitary conjugation, which is this case, you always get 1, 1.
Yeah, but A is not diagonal, right?
No, it's not. It's not.
Okay. And then why? Why is not with S? That relationship.
Okay, so all these things, they are equal to the p-norm of S, for instance. So all these things, they are always equal to the p-norm of the diagonal elements of S. This is like the invariant thing. But you may not know S, you may not know S. So for instance, in this expression for the two norms, you can compute this product and then the trace and the square root of that. You don't know what is S, but you know that the Euclidean norm of the diagonal terms of S will be equal to this thing. Right? And the nice thing about this norm, which is also called the Frobenius norm, is that it's one of the few norms of matrices that goes down to something like a vector norm of the elements of the matrix. So that's a nice property there to compute things and analytically do things. But then it's not the most useful norm when you are trying to bound stuff. So the other norm that is useful is this one, which is just the sum of the singular values. Okay. And another norm that is quite useful is the infinite norm, which is the max singular value. You see that we cover some of the norms that we introduced before in another way, but this is why I accepted p-norms, because you get these three guys that are related to other norms, but sometimes it's easier to use. Okay, so why are these things useful? Because the Holder's inequality that Mikel introduced before, which was something on the line of Q. Okay. We can do a similar thing with matrices by introducing the inner product as this. Okay, so the absolute value of the trace of this product is lower bounded by the norms of A and B. You can think of the extreme cases. If B is super small, this thing should be super small, right? So this represents somehow that knowledge. But if A is super big, then this thing shouldn't be bounded by something super small, right? So that's kind of the intuition. And now let's go to something related with quantum information. Let's say I have some observable O and two states, and I want to measure this observable in these two states. Okay? And now I want to count how different this thing can be. So this is trace of the two with one. So formally this comes from what formally? Initially this comes from sigma this, which is the same as what I wrote initially. Yeah. And now I can see this as the matrix A target, and I can see this difference as the matrix B up here, and then we have that. Right? Okay, and so a very common norm to use for P is the infinite norm, which is basically the maximum, in this case, eigenvalue, absolute eigenvalue of the observable. So the maximum value for the observable that you can observe, that you can measure, that's the infinite norm of the observable. And on the other hand, if we use infinite for P, then the only option that we have for Q is to use 1, so that this property is fulfilled. Which is the sum of the eigenvalues of this kind. And so this is a specific case where the difference between these two things can be bounded by that's right. Norms. And this property is very useful because it's telling you if two states are very similar, then the expected value for any observable will be very similar. Right? So if this thing is very small, then any expectation value will be very small. Unless you are doing, unless you are paying attention to make this very big, but please, play fair. And the other way is also true, right? If the norm of this observable is very, very small, if this observable is very, very small, you won't be able to notice many differences between rho and sigma by measuring the observable itself. And this is expressed by this thing. So if the maximum value of the observable is 0, very, very small, what information is that giving you? Nothing to distinguish these two states, right? So this inequality is basically telling you this. Okay, so this motivates the definition of this thing of a trace distance. So it's the trace distance between two states is the normalized version of this norm. Okay? We put this 1/2 here so that the distance goes from 0 to 1. Because if you can think of this eigenvalue, never mind, I won't enter into that. Okay, so this was basically the most more or less the last thing that we wanted to introduce. There is one last thing. Yeah, okay. As also Mikel mentioned that you can introduce norms, vector norms by doing inner products like this thing. Yeah, like this thing. So okay. We can do similar things also for matrices. So let's say you have some positive matrix here. You can also by using the inner product of the trace. Okay, so you can do this, for instance. But yes, this was just something that we wanted to mention if someone encounters that. And yeah, finally, just let me remember what we said. The norms in finite spaces, they are equivalent in the topological sense. So if one of them is zero, all of them will be zero, and if one of them approaches to zero, there's some limit, they will approach to zero if you keep the dimension fixed. But the problem is that often we get about bounds that have the dimension. Okay, so let's say that I know, well, I hope you are able to follow the board right now. Let's say that I know that this, that this is small. Or let's say that we know that the difference between two states is small in two nodes. But as Mikel mentioned before, this only applies for the trace node, which is the one that we care about for these kind of properties. Okay, so we are getting a dimensionality factor here when we go from the two node to the trace node. So unless you have some method to get rid of this dimensionality factor, it's very likely that the bound in the two node won't be enough for your purposes. Okay. The other way around, if you the same way, if you have a node in the infinity node, you get a fully dimensional factor here, okay, which again maybe not enough in your purposes because often, yeah. When I told you about the limit, the important thing of the norms to be equivalent in some limit is that you have to keep the dimension fixed. But if the limit that you care about is increasing dimensions, that is, increasing the number of qubits, then this could be a problem because we know that the dimension of the Hilbert space goes into 2 over n. Okay, so if you have something that increases with the number of qubits, for this limit, maybe the equivalence between norms it's not that true in practical sense. Okay, so just that warning. And I think with this we can finish. We have some notes. If you want to have them, you can get them. In any case, most of this is covered in like 2 to 3 Wikipedia pages. What we did is just to wrap them up and also introduce these motivations and these useful considerations. And that's it. So thank you for your attention. Thanks also to Mika who had to go because we have another meeting.
If you are you know one that having the infinite norm, this is fair.
What do you mean? What do you mean?
I mean, you were saying that you are trying to have some norm, if you want directly the infinite norm, maybe it's not fair because you have an infinite.
Maybe it's not here.
But if you started from the one norm, like you have an infinite norm.
Yeah. Okay. Yes. That can happen.
Or no?
Okay, so but you are having an infinite norm of an operator on states, right? So that's kind of like okay. Now you can also see rho and sigma as we explained. If you order the element wise, you can see rho and sigma as vectors in the vector space, right? And now we have quantum channels that are matrices that act on that vector space, right?
I think that will be
So, for instance, this is a random channel if it maps states to states, okay? Let's focus on that property. Then for the channel, we can also define this kind of norms. Okay, so let's define the infinite norm for the channel as the supremum of xx, and this norm, what norm do you take here? In your case, the one norm, for instance.
Yes.
Okay, so we can define an induced norm for the channel by the norms of the states. This is X because it's not necessarily a state, it could be some other Hermitian matrix. Okay? Then, as this is an induced norm, what we have is that for any X, the trace norm will be bounded by the infinite norm of T times the trace norm of 1. In particular, if you take X to be the difference between two states, what this is telling you is that the channel, the difference after applying the channel can be bounded by the linear difference between the states times something that depends on the channel. So, but this has nothing to do with this bound, because here the relevant norm for this is this, and this infinite norm comes induced by the one. The problem would be if here you were using some induced norm that depends on other B norm, but then you are trying to bound things on the one. For that, it doesn't work. Okay, so the induced norms, if you want them to be useful for one particular norm, you have to induce them by the norm that you care about. Okay, any other question or comment or something?
But it would be very useful if we know the dimension directly. It's a consistent. We are trying to find the speed. This is a possibility.
Yeah.
This is the same equation we probably use. Called Boore's dimension. Because we know the dimension and when find this norm on.
Okay.
Then you can manipulate rho sigma with the dimension of how states, so to say, and this is bounded by the energy matrix. Maybe the same thing there.
Do you mean that if you have some bound that depends on some parameter and you fix the dimension, and for some values of this parameter, this epsilon is 0, you are getting a bound also for the trace distance? Yes, that's true. In that case, this equivalence is useful and you don't care about this dimensionality thing. If what you care about is some other parameter, and if you care about the dimensionality, and if you care about other parameter, then this is fine. This equivalence is an equivalence that you can use. Okay. I think we have to leave. So, thank you.
Thank you.